Okay, good morning, everyone. Dr. Nat here. So we are continuing with discrete probability distribution. So far, we're covering discrete. Later on, we're going to continue on continuous probability distribution. So what have we covered so far? We have covered about discrete uniform distribution. We know that the probability is the same for all the random variables. And for the binomial distribution, we know that the outcome should be either a success or a failure. And it doesn't matter if you have like 10 choices, you need to pick one, and that one correct choice is the success. And the rest, which is the 9 other choices, will be the failures. And for Poisson, we haven't covered that one yet, I believe. So we talked about some of the applications for discrete probability distribution. And this was like just a walkthrough. Binomial distribution is used a lot in experiments because as you all know, we know when we're talking about experiments, we want to know whether it succeeds or it fails, anything in life really. So binomial distribution has a lot of applications. You can think about this for your future projects that is coming soon. And we only covered binomial so far and discrete. Okay, so remember that for the probability mass distribution for a discrete uniform distribution is like this. The probability is uniform across the random variables. It doesn't matter how many random variables that you have, they will have the same probability. So if you have 20 random variables, then your probability will be 1/20. Your n is this guy. So 1/n is your probability. And this is how you plot the probability mass function. So if I ask you, I tell you, given a discrete uniform distribution, plot the probability mass distribution. This is how you would plot it. A lot of people did not do well in the plottings. So let's try to focus more on that because it is very important for you to know how to plot graphs, how your graphs are supposed to look like. In statistics, at least. Okay, so we talked about when a fair dice was tossed. We know that dice has 6 outcomes, and therefore for each number, whenever you roll a dice, each number will have the same probability. For example, you roll a dice, you get 2, it has a probability of 1/6. You roll a dice again, you get 5. That one has the probability of 1/6. All of them has the same probability because they are independent of each other. Getting one outcome does not affect the other outcome. Okay, so we also talked about its equation for mean and variance. And for the first attempt that we tried to calculate the mean and variance, it was a very lengthy equation, which was the summation of all the numbers over the total numbers. So if you had like 1,000 numbers or 1,000 random variables, this would be a pain, right? That would be a pain. Therefore, they have a simple equation which you can use, which consists of B plus A. And you have to know what B is and you have to know what A is. So the condition to use this equation is that the random variables must be integers that are consecutive, happen in a consecutive manner. For example, if you're talking about dice, the numbers are 1, 2, 3, 4, 5, 6. The numbers are consecutive. They do not have any missing numbers. You're not skipping numbers. So this is the condition. It has to be in a consecutive manner for you to be able to use this equation. So if you have like 48 random variables, you have to have 1, 2, 3, 4, 5, up until 48. No skipping numbers. Why is my pen like this? Okay, so this is what's the condition. So if you have 48 random variables, which goes from 1 to 48, so B will be 48 and A will be 1 divided by 2. So this is your mean. Mean can also be represented by E in bracket capital X. So if you see EX or if you see mu, it means the same thing, which is mean. And then we have variance for X. Again, you have to know what B is and you have to know what your A is. And this is the shortcut version. I recommend you to use this one. Do not give extra headache to yourself. because we have already a lot with statistics. Okay, so if all the values in the range of random variable are multiplied by a constant, which means that your number, instead of going for 1 to 48, you decide that, okay, the random variable is 2 to whatever the multiplication that you choose, without changing any probabilities. The condition here is that the probability must be the same. The mean and standard deviation are multiplied by the constant. So please try to apply this in your exercises later and see how it affects your results. Okay, so moving on to binomial distribution. Again, this is just recap. So an experiment that consists of repeated trial. So just now we were talking about discrete uniform distribution. I told you that the random variable has to have a number that is in a consecutive manner for us to use the shortcut equation. But for binomial distribution, the condition is that your trial must be repeated, must be repetitive. You cannot do one trial today, tomorrow another trial, next week another trial. So the binomial distribution cannot be applied. It has to happen within the same time frame, or within the same time frame. Okay, so an experiment that consists of a repeated trial, each with only two possible outcomes, like I mentioned to you before, success or failure, non-defective or defective, on or off. Now, the tricky part to binomial distribution is that the question can rephrase a failure. Sorry, it can ask you to assume that a failure is a success. For example, I want to know, okay, let's go over this one. A worn machine tool produces one defective parts. Let X be the number of defective parts. But in binomial distribution, this would be your success. Sorry. Oops, what happened to my slide? Okay. So in binomial distribution, the number of defective is your success, while the number of non-defective is your failure. So it's flipped, right? So it depends on the question. You have to know which one is considered the success. So if they are asking for the number of defective parts, then that will be your success. So you apply that success in your binomial distribution or in your equation. And then you have to know that binomial distribution, sometimes they give you the P, sometimes they do not. And number 25 parts produced is your trial or your repeated experiments. So this happens with in the same time frame. Okay. What else do I want to cover here? I think we're good. Okay, and then we also talked about multiple choice experiment, and I told you, even though that you have 4 choices, if you have A, B, C, and D, if C is the only correct answer, then only C is your success, while the rest is failure. Even though you have 3, doesn't matter. So this will be your success, assuming this is the correct answer, and whatever other choice that you choose will be your failure. It is also often reasonable to assume that the probability of a success in each trial is constant. Okay. Okay, so the notation for binomial distribution is the random variable X is binomial distribution NP, where N is the number of trials, P is the number of probability. Now remember, when we're talking about binomial distribution, we are talking about sample from a large population, and the sample must be 5% of the total population for this binomial distribution model to be successful or to be accurate or to be close to accurate. Let's say you are doing a survey and you want to, you want to present your data in binomial distribution. So you have to have this in mind. the 5% of the population. This is the condition for a good binomial distribution. Okay, so if X is a binomial distribution trial N with probability P, the probability mass function of X is given by this equation, which is the same as our combination equation. So sometimes they abbreviate this as N choose X. N choose X. So it becomes like this: 1 minus P. Oh my God. I think I probably need to change my pen. It's not working well. 1 minus P N to the minus X. Okay. Okay, so if you see this, don't get confused. It's just the combination equation, which is applied in the binomial distribution. This is for X equals to 0, 1 up to N. Otherwise, your probability mass function is just a 0. This is the same as before that we have learned so far. Okay, so if X is binomial distribution with N trial and P probability, then the mean and variance of X is given by mu of X or E of X N times P. And the variance is NP times 1 minus P. Okay. This was the example that we went over last time. The probability that a certain kind of component will survive a shock test is 3/4. So this is our probability. Find the probability that exactly 2 of the next 4 components. So your 4 is the number of your trials. So this will be your N. And exactly 2 is the number of X. So N choose X. N choose X. 4 choose 2. And then the rest is just your equation. P to the X. 1 minus P N minus X, if I'm not mistaken. So the only tricky side to this is understanding the equation. I think for statistics, that's the most tricky part. And also remembering the equation, which is a lot. Okay. Okay, we already covered this one. Did we do this one? Yes. Okay, so this is a new example. So hopefully everyone remembers what binomial distribution is by now, because I already did a recap, which was quite long. So the probability that a patient recovers from a rare blood loss is 0.4. Okay, so this will be our probability, right? If 15 people are known to have contracted this disease, what is the probability that at least 10 survive? Okay, so I want everyone to help me on this one. So if P is 0.4, what is my X and what is my N?
N 15.
N is 15, correct. What is my X?
N.
X is 10. So is it like this? Would this suffice? Is this correct, everyone? So at least does not mean anything? What does at least mean?
More than 10. More or equal to 10.
More or equal to 10. So instead of using the equations, this sign, it should be at least. So X must be greater or equal to 10, because at least means 10 is the minimum. So X must be greater than 10. Okay, so I think that's correct. What about B? From 3 to 8 survive. What is our N?
Three until 8.
n. That's your n. 3 until 8. 3 until 8. So what would be the sign? Is it like this? 3 until 8. Is this correct? What is our n?
and still 15.
N is still 15 because that is the number of trials. From 3 to 8 is what we're choosing, right? So what we're choosing will be the x. So n is still 15. And x will be from 3 to 8. So x will be from 3 to 8. 3 to 8. It will be equal to 3, and it will be it will be greater and equal to 3, and it will be less than or equal to 8. Okay, I think this is correct. What about C? N is still 15. What about the X?
X is 5.
X is equal to 5. There's no less, there's no more, because we are talking about exactly 5 survive. So if I were to write this in binomial, let's try to do that. X, that, binomial, and our n would be 15, and our p would be 0.4. So this applies to all A, B, C, because here from A, B, C, the only difference between them is the x, what we're choosing as our x. So another way to write this is the generalized binomial distribution notation. You can also write it like this. Or should we just go for this one? P is equal to less than 10, sorry. Probability of x greater than or equal to 10. And we have the binomial distribution like this. Px equals to whatever x that we choose equal to the combination and also the rest of the equation. Excuse me. Okay, so that would be n is 15, choose 10. P is 0.4 to the power of x, where x is 10. 1 minus p, which is 0.6. Okay, 0.6, sorry. N minus x, n is 15, x is 10, so n minus x is 5. Is this correct? Is this correct or not? For A. Come on, guys. This is 15, choose 10. Is this correct or not?
Yes.
Why is it correct? So no one knows? Okay. Okay, so, let's go over the equation again. Okay. So here, look at the equation carefully. So this is probability of x equal to whatever number that we choose. Equal, not greater than or not greater than or less than. So if we have something like this, we have to like rethink this problem. So this equation would apply for C, exactly 5 survive. So let's change this. So x is equal to, this would be equal to 5 and 15, choose 5 and 0.4, and this one would be 0. Oh, this is the same, sorry. 0.6 n minus x, n is, no, this is p to the power of x, and this is 1 minus p to the power of n minus x. N minus x, n is 15, x is 5, so this will be 10. Yeah. Okay, so only C satisfies this equation. I mean, can use this equation because it is exactly 5. So how do we do the ones that is greater than 10 or less than, or something that is between 3 and 8? So let's look at the solution. Okay, so for you to know for you to find out what is the probability of X being greater or equal to 10, 1 minus probability of X being less than 10, which is this guy. The binomial distribution from 0 to 9, which is a lot. And N, this is your N, 15, and this is your P. This is another way of writing binomial. They have, first we had this version, which was, oh my God, this is testing my patience. Okay, bin. Oh, I need to upgrade this. Okay, bin. And P, right? Okay, another way to write this would be B, whatever X that you choose. For example, we are choosing 5. So you write in 5. You have your semicolon there. 15 is your N, and you have your P as usual, NP. But the only thing that is you have your X over here. So this is more the general notation of binomial. This is if you want to be specific with the number of X that you choose. Okay, both are correct. 0.4. Okay, so obviously we don't want to do this calculation. So let's see if there is another way to do this. Of course, there is another way. We are engineers, so let's use Excel. So we want to know the cumulative, right? If we were talking about probability mass function, we are talking something that is exactly X equals to 5, X is exactly 4, X is exactly 3, that is probability mass function. But when we have summation, we're talking about cumulative probability mass function, which I hope everyone knows at this point. So the same case applies for binomial. So let's use Excel because I don't want to do the equation. So how would we do this? Let me share my screen. Stop sharing. Okay, I want everyone to look here. Let me share first. Oops. Share. Okay, I'm going to teach you how to use binomial, and hopefully you can use this to help you study, check your answers, see different approaches to the problem. So equal sign, this is Excel by the way, equal sign, binomial. So here you have binomial distributed range, binomial, we're not going to cover this one yet. Let's just talk about the binomial distribution, the regular one. So this is binomial distribution. So how do you know how to use this equation? When I write in binom, it gives me a list of functions. I click on this guy over here, and I have something in blue and something in black, right? So if I click on the blue thing, let me make this bigger. Don't know why it's very small. Make it bigger. Okay. So hopefully this is big enough for everyone's eyes. Okay, binomial distribution. Click on it. Okay, so here they tell you how to use it. Binomial distribution function returns the individual term binomial distribution probability. Use binomial distribution in problems with fixed number of tests of trial. This is our N. When the outcomes of any trial are only success or failure. This is the condition to use binomial distribution. You can't have other than that. And the probability of success is constant throughout the experiment. We have a fixed probability P. For example, binomial distribution can calculate the probability that 2 of the next 3 babies born are male. A very weird example, but let's just go with it. Okay, so here the syntax is binomial dot distribution number of trial. Sorry, this is number of S. Number of S is the number of success. This is your X. This is your X. Okay, and then the next one is trial. This is your N. And probability underscore S is your probability P. And here you have the word cumulative here. So if you write in true, you would find out the binomial distribution, the cumulative version. And if you write in false, you would get the probability mass function, which is x equal to 5, x equal to 4. But if you use the cumulative function, you would get x less than 5 or x greater than 5, like that. Okay, so let's see how we can use it. So I want to know what is my probability of getting x equals to 5 from the previous problem. So let me stop sharing. Let's go back to the question again. This feels like teaching AutoCAD suddenly. Okay, so this is what we have. We want to know exactly 5 survive. We have 15 people. We want to know x equals to 5. P, what was our P again? Our P is 0.4. And we want to use probability mass function, not cumulative. So let's go back to our Excel. Are you still seeing my screen for Excel? Yes or no?
No, doctor.
Okay, let me stop sharing. Okay, are you seeing it now?
Yes, doctor.
Okay. So our number of trials was 15. I feel really bad about the example, but this is math. Trials is, sorry, this is our x, sorry, forgive me. So x is equal to 5 and our trials is 15 and the probability is 0.4 and we want to know our probability mass function, not the cumulative. So we will choose false or you can just type it in false like that. Doesn't matter, you can choose like this or you can type it in. So I would get 0.1859. So let's see if that is correct. 0.1859 is your answer. Okay, so this was using using Excel and the probability mass function. There is also another way to do it, which is using your cumulative distribution function. So here, how would you approach this if you were to solve it using cumulative? Is that you would find out what is 0 to 5, which means that your x is less than or equal to 5, minus with x less than or equal to 4. Okay, so you would get only the portion of x equals to 5 when you do that. Of course, this is like the lengthy way to do it, but sometimes it is needed. So I'm just telling you guys, there's another way to do it. Okay. Let's go back to A and C now, A and B now. So now we're talking about at least 10 survive. So how would we do this? X is greater than or equal to 10. So the way to do this is I would write it like this: 1 minus the probability of x less than 10, because no, actually I would use cumulative, but it's okay. Let's just follow the solution. So this would be equal to 1.
Sorry, doctor. Are you presenting the slide right now?
Yes.
Because I'm seeing Excel.
Okay, sorry. Forgot. Okay. Okay. So I'm talking about A now. So now we're talking about x being greater or equal to 10, which is equal to 1 minus p less than 1 minus probability of x being less than 10. So if we were to use cumulative function, it would be 1 minus the summation from 0 to 9 binomial distribution x, 15, and 0.4. So how do we do this in Excel? Let's do it. So I want to know from 0 to 9. N is 15 and P is 0.4. So the cumulative goes up to 9, not 10, because it must be less than 10. There's no equal sign here. So I'm only going up to 9. Okay, now I need to stop sharing and share again. My Excel, okay. So why am I teaching you this? Because obviously you will use this for your projects and also to use this when you are revising. You can double check your answers. Okay, so we want to know what is cumulative from 0 to 9. Binomial distribution. So number of x will be 9. And the number of trials is still 15. The number of probability is 0.4. And we are choosing cumulative now. Oops. I'm choosing cumulative distribution function true. So the answer is 0.966. So just now we saw that we had to use 1 minus probability of x being less than 10 to get probability of x being greater than 10. So it would be 1 minus whatever answer that we got just now, which was 0.966. And the answer is, the final answer is 0.0338. Okay, so why do they teach you, why does the solution tell you about cumulative? Because Excel only lets you find out cumulative functions. And it doesn't let you to calculate from 3 to 8, not like that. So it only tells you x less than whatever number that you have, only that version. So even if you have x is greater than 3, x is less than 8, you have to rephrase the question to be like this. Okay, so this is why the solution is like this. So 0 to 8 minus with 0 to 2, because your x is going to be 0. You have to, you have to use the Excel. You have to rephrase the question in a way that you can use Excel if you're using it that way. Okay, so 0 to 8 minus 0 to 2. Let's do that. This was when x is up to 9. X is equal to 5. You don't remember what this was about? Now we're trying to find out x up to 8. Binomial distribution. Number of s is 8. We are going from 0 up until 8 because the x is less than or equal to 8. So 8 is in the equation because it is also equal to 8. And then we have our trial as 15 and our probability as 0.4. And we are using cumulative, which is true. So this is 0 to 8. And then we calculate x 0 to 2 by norm. After this, I'm going to have a break. I mean, we are going to have a break because I need it. What was it? 2. Trial is 15, 0.4. And this is going to be true because we are finding the cumulative. So this is x from 0 to 2. Now, when I subtract this guy with this guy, what I'm getting is something that is between 3 up to 8, which is the question. So this is, so the answer is 0. X is between 3 to 8. 0.877. So let's see if we got that. Sharing my screen again. So this is the answer. Okay, so you can try this. Whenever you're doing exercises, you want to know what's the answer, the correct answer, you can use Excel to help you. So did everyone get that? Was that okay?
Okay, doctor.
Does anyone have any questions so far? No questions? Okay, let's take our break. Let's take a 7-minute break. Let's come back at 9:50. Okay. Okay, see you in 7 minutes. Oh no, Oh, by the way, if you are shy to ask questions because our class is very large, you can type in your question to me so I can answer it privately, or I can answer it to the class, but you can ask me privately in the chat box. So that also works with me if you're too shy to ask. Okay, so I'll see you. Bye-bye. Whoops, I overboard time. What did I want to say? Is everyone back yet? I want to share the pictures.
I'm here.
I want to share the pictures from my glamping trip. Okay, let me share my screen. So anyone who is already following me on Instagram, you've seen this. So just bear with me. So this is in Kuala Kubu Baru, which is in Selangor. 1 hour and a half from UPM. So we had to use this type of, we call this rakit, as our means of transportation, very traditional. And this was us trying to get our luggage from one point to another. So this is where we had our swimming session. And this is where we slept, just kidding. We slept in that thing over there. On the floor with sleeping bags, no fans, no electricity. We had to use power banks. And we had like swings. Oops. We had swings over here. So, I mean, you could dive from the swing, but I wouldn't recommend that because of injuries. And this was one of you asking me, do we still have class tomorrow? Because I'm still from camping. We do have class today. And this is actually my students from my photonics lab. So if you graduated and you want to join our lab, I welcome you to our lab. We study about optical fiber. I specifically use optical fiber as lasers. There are other branches of the study in using what do you call it? Developing sensors. I do that too as well. I also use IoT and integrate it with the optical sensors for detection. Of course, this is why I'm in the department, because optical fiber is part of communication. Yes. So this was the entire gang that went for the trip. Again, this is from the department. Okay, this was the instance where I fell into the water. We were trying to, transport ourselves to the other side of the water. And we were saying we are great women. And then I fell. So this was them panicking when I fell into the water. But of course, I am a very good swimmer. No, not good swimmer. I have good upper body strength. So I could actually, So I could actually hold on to the rope. Just kidding. I don't have that great upper body strength, but adalah sikit. So that was it. The end of my trip.
Nak pergi juga, doktor.
Kita buat trip lain. Let's make another trip. But I don't know how feasible that is. We could like rent a bus. We could.
Boleh, doktor, kasih jadi.
What? Excuse me?
Boleh, doktor, kita buat nanti. Kita buat habis test ke. Boleh lah. Nak pergi doktor, nak tengok doktor jatuh lagi.
I don't want to fall again. But okay, let's try for that. If you have any other lecturers that you are in good terms with, we could also plan the trip with them later on. Okay, so I have some chats here. Let me see. Oh, it's just people laughing. Okay. All right. So let's continue with class. That was just a distraction. Keep you guys awake. Let me share my screen again. Where is it? Okay, so back to the presentation. So binomial distribution, again, we have two outcomes, either success or failure. And we have n number of trials, and also P is our probability. We can use Excel to help us find binomial distribution. And specifically using Excel, you have to rephrase the question in a way that you find the cumulative version, which is x less than something. So if x is less than 8, your cumulative will be x equals to 8. And if x is less than 2, it will be equal to 7 because it's less than 8. So if your x is less than or equal to 8, then your x in the Excel equation would be x equals to 8. So this is specifically for Excel only. I don't know how to use R. I'm not familiar with R, but you can explore if you would love to use R for your project later. Okay. All right. So this is binomial distribution for selected values of n and p. So here we have n 20 trials and the probability is 0.5. As you can see over here, with a probability of 0.5, the distribution is quite symmetrical and it looks nice, right? Whereas for the next graph, we have n as 10 trials with probability of 0.1. This is indicated by the darkened bullet. So our distribution looks like this. Let me use a different color for the other guy. And 10 trials with a probability of 0.9 goes from here to here. I'm just making it obvious to you guys. So one has a probability of 0.1, which makes it skewed to the right, right? Skewed to the right. This guy is skewed. And one with a probability of 0.9. So it is skewed to the left. So here they're telling you for a fixed n, the distribution becomes more symmetric as p increases from 0 to 0.5. So you saw that when your probability was 0.5, it was very symmetrical versus 0.1 or 0.9. So if your probability approaches 0.5, no matter from this side or this side, so this is 0 and this is 1, it will become more symmetrical. So 0.5 is like the ultimate probability to get a symmetrical graph. And for a fixed p, meaning to say that your probability is fixed, but you can change your n. The greater your n, the better the more symmetrical your distribution. So let's see if I have an example of that, or we do. So here we have the binomial distribution with n number of trials and the probability of 0.4. So 0.4 is close to 0.5. So we have a rather symmetrical distribution. And then, oh, they didn't compare between n's. Here we have binomial distribution, 20 trials with 0.1 probability. So 0.1 will be skewed to the right. And this is your 20 trials. So you see that it is quite symmetrical, but on the one end of the spectrum. So the greater number of n's that you have, the better your data, because basically you are taking more data. Okay. All right, so that was the end of binomial distribution. I hope everyone understood what we did so far. So the next one is Poisson distribution. Again, a French guy, that's why it's pronounced like that. Arises frequently in scientific work, is an approximation to the binomial distribution. So here it is related to the binomial distribution, but when the binomial distribution has n that is very, very large, then we use the Poisson. For example, a mass that contains 10,000 atoms of a radioactive substance, the probability that a given atom will decay in a 1 minute time period is 0.002. So the probability is very, very, very small. The probability that we were talking about just now was like 0.5, 0.8, 0.9, which was quite large, right? So here the probability is 0.0002. So very, very small, and the n is very, very large. It's not 10, it's not 20, it's thousands or hundreds. So this is when you use the Poisson. So let X represent the number of atoms that decay in 1 minute. Now each atom can be thought of as a Bernoulli trial, independent trials, where success occurs if the atom decays. Thus, X is the number of success in 10,000 independent Bernoulli trial, each with success probability of 0.002. So the distribution of X is binomial, 10,000. This is your N, and this is your P. Basically, it's the same thing, except your N is super large and your P is super small. So the mean of X is mu, or EX, equals to NP, same equation as binomial. And the variance of x is same equation as binomial. So far that we're talking about. So this is NP and this is 1 minus, oh my God. This is N minus P. 1 minus P. And P, the product of N with P and 1 minus P. So this is your variance. If you want to find out what is the standard deviation, of course, just use the square root. You would get your standard deviation. Someone did a mistake on this one as well in the test. Okay, so bear with me. That was the first example. Now this is the second example. Another mass contains 5,000 atoms. Just now it was 10,000. And each of these atoms has a probability of 0.004. Just now it was 0.002. So this is like times 2, and this is like divided by 2. And the same situation of decaying in a 1 minute time interval. Okay, let Y represent the number of atoms that decay in 1 minute from this mass. So by the same reasoning in the previous slide where we found out what was the mean was NP. And the variance was squared. Oh my. This is NP 1 minus P. Okay, NP 1 minus P. So same case over here. So the binomial distribution, 5,000 trials with 0.004P probability. Therefore, your mean is 2 and your variance is 19.992. Now let's compare with our previous example. Did we get the same answer? The mean is 2 and the variance is 19.996. Let's see, 19.996 and 2. So it's quite, it looks the same, right? So in each of these cases, the number of trials N and the success probability are different. Again, this is 5,000. The previous one was 10,000. This is 0.004. The previous one was 0.002. But the mean number of success is equal to NP is the same. So what about its probability mass function? So let's see. So if N is large and P is small, and we know that this is the equation for binomial distribution. Let's say lambda is NP. So this is the Greek letter called lambda. Let lambda be NP. So if I were to use the binomial equation for the probability mass function, and I substitute P with lambda over N into my equation, okay, into this equation, let's see what happens. So I'm substituting P, I'm getting rid of P from this equation. So N choose X, P is lambda over N to the power of X, 1 minus lambda over N to the power of N minus X. So again, Poisson distribution deals with N that is very, very large. Now we can assume that N approaches infinity for our equation, just for our equation, not for the question, because we want to do an approximation. So assume that N approaches the limit of infinity. Therefore, we can say that N is very, very large here, and we can assume our P is very, very small. So this simplifies to this equation. So if N is very large, well, the proof is in the textbook. I'm not going to go over it. It's quite lengthy. So let's just try to remember this equation, which is fairly simple. It's e to the power of minus lambda. Again, lambda is NP. And then lambda to the power of x. X is the number that you choose, and over x factorial. Okay, so a condition where when you use Poisson distribution is that your x must be an integer that is not negative. It must be an integer that is not negative, or a non-negative integer. Otherwise, your distribution will be 0. Your equation for this guy, this equation will not hold. You cannot use it. So x is a discrete random variable whose possible values are non-negative integers. The parameter lambda is a positive constant, and p, The probability mass function of X is given by this guy. The Poisson probability mass function is very close to the binomial probability mass function when n is very large and p is very small. And again, lambda is equal to np. Okay, so Poisson is just like an extension of binomial. So how did the French guy came about this equation? So he was working with what do you call this? A beer company, and they had like a problem whereby they couldn't figure out, I don't remember what was the story. They couldn't figure out how much concentration that they had to use or something like that. But the following example will talk more on this. When n is large and p is small, oh sorry, this is not the example yet. So we're just trying to compare between binomial distribution and Poisson. So when n is large and p is small, the binomial distribution NP probability mass function is well approximated by the Poisson lambda probability mass function with lambda being equal to NP. Okay, this guy is NP, the product of NP. So here, when X is binomial distribution 10,000, 0.02, and the second example that we talked about was 5,000 with 0.004 probability. Therefore, your lambda was 2, which was the same for both, right? This is equal to 2, and this was also equal to 2. Even though they had different values for n, different values for p, it didn't matter because the lambda is still the same. Therefore, you could use the same Poisson distribution for both of these problems. So here, they are using Excel, obviously, to calculate what this is. So you will find out that this guy is the same as the value for this guy, as value for this guy. It's not accurate, but it is approximately the same. You can see there are slight differences. For example, 0.135308, 0.13528. So slightly different, but close. 0.135335. Again, it is close. So you have two problems whereby the lambda is the same. You could just use this guy and solve two questions at once. So let's try to figure out how to use Excel for the Poisson distribution. Yeah, okay. So let me stop sharing first. Share screen. Okay, so moving down a bit. So this, again, equal. When you put in equal sign, it means you are entering a function. What was it? Poisson. So PO, this is your, how you spell Poisson, .dist, which is distribution. Click on that. Here, let's click on the blue link. So the Poisson distribution function returns a Poisson distribution. Obviously, a common application of the Poisson distribution is predicting the number of events over a specific time, such as the number of cars arriving at a toll plaza in 1 minute. Okay, so here your X is the number, oh, I can't see it. X is the required, sorry, X is the number of events. Mean is your lambda. And cumulative is, again, you have your option for true or false. If you choose false, we're going to find the probability mass function for Poisson. If you choose true, you are going to find the cumulative mass function for Poisson. So if X is not an integer, it is truncated. So let's say you put in 1.2. The Poisson distribution does not recognize this because, again, to use Poisson, it needs to be an integer. So it will truncate it to become 1, something like that. If X or mean is non-numeric, Poisson distribution returns the value error. So if you get error, you're using it wrong. If X is less than 0, again, error. If mean is less than 0, mean is NP, also again, error. For cumulative equals to false. This is your equation, which is the probability mass function. For cumulative true, this is your equation for Poisson, which is the summation from 0 to X. Okay, so again, if you don't remember what the function is, click on the blue link and read it. Okay, so what were we talking about for the Poisson? We were talking about the mean was NP. It was 10,000 times 0.004, which was 2. Our X is, wait, we don't have an X yet. Let me stop sharing. Or should I go with the example? Excuse me. Oh, sorry, this is the X. X is 0. This is our X. This is our NP, which is our mean. Only 2 things that are required here. So let's see, 0 and 2. 0 and 2, and we are trying to find probability mass function, so it should be false. So this is 0. X is equal to 0. Mean is 2. And false. So we're trying to find the probability mass function. Can X be 0? Let's see, 0.1353. So let's see if we got the same answer. Stop sharing. Share. So I got 0.1353, which is the same. So again, you can use Excel to double check on your work. Okay, moving on. Does anyone have any questions? So everyone's okay, right? So let me continue. So if X is Poisson 3, again 3 is lambda. Lambda equals to 3. Okay, kejap. Give me a minute. Oh, okay, it's here. Okay, never mind. Okay, so X is equal to 3. X is equal to 3. Sorry, lambda is equal to 3. Compute X equal to 2, X equal to 10, X equal to 0, and X equal to -1, and X equal to 0.5. Which of these will give me an error? Which one? What is the condition to use Poisson distribution?
Not 0 and not negative integer.
Not 0
And
and
also
not
integer only.
a non-negative integer. Okay, so that would mean this guy will give me an error and this guy would give me an error. So let's see what happens in our Excel. So X equals to -1, X equals to 0.5. Stop sharing. Okay, so Poisson distribution, oops. Okay, yes. Poisson distribution, X is, what was it? -1. The mean was 3, which was your lambda. And we are trying to find the cumulative or the probability mass function. Which one is it? Cumulative or probability mass function? Let's go back to the question. Okay, is this cumulative or probability mass function?
Probability mass function.
Probability mass function. So again, this would be false because the default is cumulative. So this would return me an error. So what if I put in 0.5? Wouldn't give me an error, but it would truncate the answer. So it would truncate the answer to, I think it would truncate it to 0. Let me try that. Poisson. Oops. Poisson distribution.
Doktor,
X is 0. Yep.
doktor tengah buat essay tu.
Oh, you can't see it. Sorry. Okay, so here previously I tried to find the distribution when it is 0.5. Earlier on, I did it with -1. -1 returns me an error like that. So this is your error because you put in x as -1. Poisson does not deal with negative integers. So what if we had the x equal to 0.5? The function told us that it would truncate the value. So I'm guessing that it truncates the value to 0. So let's see if that is correct. So this is the answer. So Poisson distribution, x is equal to 0. The mean is equal to 3 and false because probability mass function. So even though I put this as x equal to 0.5, it returns the same answer as if x is equal to 0. So if you put in something that is not an integer, it will truncate it. What does truncate mean? It cuts off the extra piece of the number, if that makes sense. Okay, so stop sharing. Let me share the presentation again. Okay, so the rest, this one is simple. If we were to use the manual way, which is needed in the exam, we have to use the equation Px okay, x equals to 2 and Poisson of 3. So that this would be e to the power, this is supposed to be an e to the power of x, e to the power of minus x. Let me go back to the equation. It's this equation, e to the power of minus x, sorry, e to the power of minus lambda, my bad. Lambda to the power of x over x factorial. Oh, I can't remember. E to the minus of lambda, lambda to the power of x, okay. E to the power of lambda, lambda to the power of x. Lambda, sorry, 3. Okay, 3 to the power of x. X is 2 and over x factorial, which is 2 factorial. So use your calculator, fairly easy. You have your function e in the calculator, or you can use e equal to 2 point, this guy over here. But don't memorize this, just use your calculator while add a headache to yourself. Okay, so that is how you expand the Poisson distribution. You have to know what your NP is or your lambda, and you have to know whether this is x equals to something or x less than something or x is greater or less than. You have to know how to rephrase the question. So this is your answer. So anything other than, Excel still gives us the answer because it truncates this guy. But in reality, it should give us a 0 because remember this one, otherwise gives us a 0. So if you're using Excel, then you would get an answer. But if you're doing this manually, just write 0 because otherwise it's supposed to be 0. Okay. So now we have a slightly difficult question. Not that difficult. We just have to know how to rephrase this. So if x is Poisson distribution 4, you know that your lambda is 4 here. Okay, lambda here is 4. Compute probability of x being less than or equal to 2 and the probability of x greater than 1. How would you rephrase this so that you can use it in your Excel? Cumulative distribution. How would you write this? So A is Px less than 2. Well, less than 2. So how would you write this? Let's assume we are in Excel. So Poisson distribution, P, whatever that is, distribution. Oh, this pen is killing me. So X is, what should be my X? What should be my X here? Is it 2 or 1? Come on, guys, this is supposed to be easy. Should I call names? Since everyone is sleeping. Okay, let me call someone.
No.
Not sleeping. Okay. Akmal Mirza, are you there? Akmal Mirza. So Akmal Mirza is sleeping. Earth
Yes.
Akmal.
Yeah.
Okay, thank you. Okay, so you are here. So if I were to use this in Excel, I would use the function Poisson distribution. What should be my X? Akmal, don't disappear. Okay, so what is X?
2. I think 2.
Okay, 2. What is my mean?
Mean.
For this Excel function?
4.
4, correct. So should it be false or true for the next parameter?
Less than false. False. I think false.
False, okay. So this is Akmal Mirza's answer. Is this correct? Is this correct or not? What was the default for our distribution in Excel? It's cumulative, right? So true is cumulative, false is probability mass function. So again, Akmal, do you want to revise your answer?
True.
True. Okay. So this is if you were to write this in Excel. Okay, thank you, Akmal, for being my volunteer. Forced volunteer. Okay, so if I were to write this manually, right? This would be cumulative from x equals to 0 up to x equals to 2. And whatever the equation for probability mass function for Poisson distribution, what was it? E to the power of lambda minus lambda, e to the power of minus lambda, which was 4. And then we had our 4 lambda to the power of x. So this guy x would be from 0 to 2 divided by x factorial. So this number also changes with the summation. So this is how you would write it if you were to use it, if you were to find it out manually. Okay, so why did I teach you the Excel and then only the manual? Because I think the Excel is easier on you guys, and then you try to relate back to this. Okay, or vice versa. To me, the Excel is easier versus this guy. Okay, so moving on to the next example. Again, I'm going to find a very lucky volunteer to help me with this one. So here we have Px greater than 2, greater than 1. Greater than 1. X greater than 1. Okay, so Excel version. Let's hear it from lucky volunteer. Let's see. Sam, is Sam there?
Yeah, I'm here.
Okay, Sam. So if I were to use Excel to solve this, what would be my X here?
Not very sure, but I think it might be 1.
Okay, so Sam is saying it's 1. What about your mean?
Mean should be same as above is 4.
Okay, and what about the function? Is it true or false?
True is that's false.
True because
Not sure how to explain.
it is true because it's cumulative, right? Okay.
Yeah.
Okay, so again, Sam, I want to ask you again, what was the condition to use Excel cumulative function? Was it was the X have to be greater than some number, or does the X have to be less than some number?
X should be greater than 0, so not negative number.
Okay, non-negative integer, correct. But for Excel, how do we approach this problem? What does the Excel calculate? Does it calculate, if X is 1, does it calculate anything that is greater than 1, or does it calculate from 0 to 1? We're talking about cumulative, right? So does it go from
Yeah.
0 to 1, or does it calculate from 1 to infinity? What does it calculate here?
In this case should be 0 to 1.
0 to 1. So it calculates 0 to 1 if you put in 1, right? So is this
Yeah.
correct?
No.
No. So how would you rephrase this? How would you rewrite this?
1
1 minus?
the equation.
Yes, 1
Is
minus
that
the
how?
equation that we had above. Correct. So very important to take note of whether it's greater or less than. Does everyone understand this? Everyone okay with this? Very important, guys. Can come out in the exam. Okay or not okay? So I'm not getting an answer. I'm assuming everyone is confused.
Doctor say come out in exam. Does that mean do we have to do exam in Excel form or have to write it?
You have to write it because the exam is physical. But this is to help you to understand the parameters. In reality, you will have to write it like this. Okay, so to write it correctly, this is for your project. This is for your exam. So we have two versions here. Okay, so 1 minus with summation from x equals to 0 up to x equals to 1. And e is to the power of minus 4. 4 to the power of x and x factorial. This is supposed to be 0. Okay? All right. So everyone's okay? No questions? So it's already 10:30. Let's take a 5-minute break. 10:35. If you have any questions, you can ask me directly here, or you can type it in the chat box, or you can discuss with your friends. Just come back at 10:35. We're going to continue with more examples. Okay, so it's 10:35. I hope everyone is back because I have more questions to ask. So we only have 47 left. I'm gonna continue with class only for 15 more minutes. Okay, so we talked about the probability mass function for Poisson, and it was e to the power of minus lambda, lambda to the power of x divided by x factorial. And the answer from the previous example that we talked about was the summation from x from 0 up until 2. Oh. Okay. Summation from x equals to 0 up until x equals to 2. E to the power of lambda minus lambda, lambda to the power of x divided by x factorial. Okay, sorry for the x. So here they expanded this equation to be like this. So e to the minus 4, which is our lambda, 4 to the power of 0 over 0 factorial plus, because we are summing, e to the power of minus 4 because that's your lambda, lambda to the power of x equals to 1, and then divided by x factorial, which is 1 factorial. And then when your x is 2, e to the power of minus 4, 4 to the power of 2 divided by 2 factorial. So you have to sum all these numbers. So this is what this equation means. And then again, this was the answer given by Sam just now. So 1 minus probability of x being less than or equal to 1. So our summation was from x equals to 0 up until x equals to 1. So they expanded it like this: probability of x equals to 0, probability of x equals to 1. This is cumulative. This is if you are breaking it down into probability mass function, because again, cumulative is made out of probability mass function. So here they expanded x to the power x equals to 0 and also x equals to 1. So this is your answer. And if you want to check using Excel, I already taught you how to do that, so you can try it later to verify your answers. Okay, so now we're going to talk about the mean and also the variance for Poisson. If x is Poisson distribution lambda, lambda is your mean, we can think of x as the binomial distribution variable with large N, small p, and lambda equals to NP. We talked about this earlier. Since the mean of a binomial random variable is NP, it follows that the mean of a Poisson random variable is lambda. Okay, so the variance of a binomial random variable is NP times 1 minus P, right? We saw this earlier for binomial distribution, this equation for variance. So what happens to this equation if our N is really big and our P is really small? So here, since P is really small, they're going to assume that P is close to 0. So they said, okay, let's just get this out and make P as 0. So now we're left with NP. So 1 minus P becomes just 1, and we conclude that the variance of a Poisson random variable is NP equals to lambda. So here, very easy, the Poisson distribution tells us that the mean is just lambda and the variance is just lambda. And your standard deviation is square root of lambda. Do not get this wrong. Okay, you have to have that square root there. So another question that you can ask me, even though you're not asking me because I don't know why, is why didn't we assume that P is 0? We assumed P was 0 here. Why didn't we assume P was 0 here? Anyone wants to guess? Okay, so the reason is if you assume that would to be 0, then you wouldn't have a number left. But since this one is just a 1 minus probability, we're just talking about probability. If the probability is super small, then we can just assume that the probability is close to 1. So this is what they are doing over here. They're not telling P is equal to 0 specifically. They're just telling you that, okay, probability is close to 1. So I should have rephrased it like that. Because we don't want our P to be 0. If not, we won't get an answer, right? Okay, moving on. So this is how a Poisson distribution graph looks like. if the lambda is 0.1, so here it is skewed to the right. And this is if our lambda is 2. So here this is very not uniform, not symmetrical, very odd looking graph. Oh, sorry. Very odd looking graph if your NP is small. If your N is a little bit greater, then your distribution looks more decent. And then if your N gets bigger, your lambda gets bigger, it becomes better it looks better. And of course, if your lambda increases bigger and bigger, your distribution would look also better. Okay, so we have an example here that relates to the brewing of beer just now. Don't drink and drive. So here the particles, in this case, is the yeast cell, because they use yeast to make beer, are suspended in a liquid medium at a concentration of 10 particles per mil. I wish I could use another example, but this is the example that the Poisson distribution guy used. So a large volume of the suspension is thoroughly agitated. So which means that it's shaking it vigorously. So let me try to draw this. So you have your beaker, assuming that this is some particles. We don't have to go with beer. It can be any chemical, basically. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're supposed to be identical, but I don't have the skills for that. So this is your solution. You have 10 particles in a volume, assuming that the volume is 1 mil. So 10 particles is in 1 mil. So if you have more volume of water, you would have more particles, because in 1 mil of water, you would have 10 particles. If you have 10 mil, you would have 100 particles. Okay, so what is the mean here? Anyone? If I have 10 particles in 1 mil and I have 100 particles in 10 mil, what is my mean? What is the average particles per mil? Average particles per milliliter. What is the average? Okay, let me try to repeat the question again. Everyone, please focus here, because this is part of your understanding the Poisson distribution. Okay, so if I have 10 particles per milliliter of water, right? And I have 100 particles per milliliter of, 100 particles per 100 milliliter of water. Let me write that down. 10 particles in 1 mil, 100 particles in 10 mil. Oh, this pen. In 10 mil. Okay, and I have 50 particles in, let's say, 5 ml. Okay, what is the average number of particles per ml? The answer is on the screen. What is the
10.
average? 10, right? So 10 is your average and 10 is your mean. So it doesn't matter what volume you have, as long as the concentration is the same, the mean will always be the same. So this was the approach that they tried to apply here. So let V be the total volume of the suspension in milliliter. Then the total number of particles in the suspension is 10V. So 10 particles per mil. If you have a 5 mil, then it would be 10 times 5, 50. If you have 20 mil, it would be 10 times 20 mil, which is 2,200. Sorry, it's 200. So if a particle succeeds if it is withdrawn. Now, 1 mil out of the VML is to be withdrawn. So it follows that each particle has a probability of 1 over V being withdrawn. But the important part here is to know what is the mean, which is 10. No matter what the volume is, you know that the mean is always going to be 10 because the concentration is the same. So let X denote the number of particles withdrawn. Then X represents the number of successes in 10V. So 10V is your N, your trial number. X is the number that you want, right? Each with a probability of 1 over V success. This is your P. Therefore, if we were talking about binomial distribution, it would be binomial distribution. This is your N and this is your P. Whoops. Okay, but if we were going to talk about the Poisson distribution, we wouldn't care about what NP is. We just want to know what is the mean, which is just 10. So thus, to a very close approximation, Poisson distribution is 10. So if I wanted to know what is the probability that exactly 8 particles are withdrawn from a total volume, let's say 100 in 10 mil, I want to know what is the probability of taking 8 particles. So I'm choosing 8 out of the total volume, right? So since V is very large, 10V is large and 1 over V is small. So the probability of X equals to 8 is this guy. Let me try to repeat the explanation again. Okay, so we were talking about the mean, right? We were talking about the mean being 10 because why do we know the mean was 10? Because 10 in 1 mil is, this is the concentration, 10 per mil. In 100 particles in 10 mil, so the concentration of the particles in this large volume is still 10 particles per mil. How did I get this? 100 divided by 10, and then 50 divided by 5, 50 particles in 5 milliliter of water. What is the particle concentration per milliliter? It is still 10. 50 divided by 5 is just 10. So this was our mean, which is lambda. Okay, lambda is 10. So we already know Poisson. How do we relate it back to binomial distribution? How do we know what is N and what is P? So here they are telling us, let V be the total volume of the suspension in milliliter. So they're not specifying how much, they're just telling you V is the total volume. So if you know that the concentration is 10 per mil, let's say you have 100 mil, you can just simply divide it, multiply it with the concentration. So let's say V is equal to, let's use a good number, 3. I hope this is a good number. Therefore, the total volume, the total number of particles in 3 ml of water, this is your total number of water, right? Is concentration times with volume of water. What is the unit for concentration? It is particles per mil. What is the unit for volume? It is mil. So this is in milliliter. And, oops, sorry, this is supposed to be like this. And concentration is, I'm going to write it as CON. And it is particles per mil. Okay, so if I were to, the total number of particles in the suspension is 10V. So it's saying that the concentration times volume, this is V. Our concentration is 10. This would give me 10V, right? What does 10V represent? 10V represents the number of particles. If you cross this out, the mil crosses out with mil, I would get 10V particles. Okay, so this is the number of particles. Now, I want to know what is the probability of choosing just 8? Just 8 from the 1 mil, that I withdraw. So if this is our N, because this is the total number of trials, the probability of selecting particle is 1 over V. Okay, so your binomial distribution would be NP. N is 10V and your P is 1 over V. Therefore, your NP would be just 10, which is concentration. So if binomial is more attractive to you, you understand binomial better, go for binomial. If you understand Poisson better, go for Poisson, and vice versa. You try to relate these two together. Okay. So hopefully that was a better explanation. I don't know how else to tell this except for examples later on that we're going to do. But we're already out of time. So let's continue this example in next class. I'm going to finish up Poisson and then start with the geometric in the next class for tomorrow. Okay, I'll see you guys tomorrow. Have a great rest of the day. Don't forget to eat your lunch. Take care. Yeah, see you tomorrow. Bye-bye.
Thank you, Doctor.
Thank you, Joshua.
Maunya.
Doctor.
Bye.
Thank you, Doctor.
Thank you, Doctor.
Bye.
Thank you, Doctor.
Welcome. Bye-bye.